And my talk today is a bit of history, as the title says. And I picked the significance of ABX3 compounds because I've worked on a number of these over the years. And I think they have really interesting implications for mineralogy and earth science. And sometimes A and B are the same cation, and I'll be talking about those compounds. And X can be oxygen or sulfur, could be selenium and tellurium, but I'm going to talk mostly about oxygen and sulfur as the X anion. So let me go on. The history of research focused on ABX phases. ABX phases, the ABX3 phases, have been involved in all of these items that I list here in this table. Discovery as minerals originally, synthesis in the laboratory, phase relations, application to geological problems, measuring of physical and chemical properties, crystal structures, determination and applications, high temperature and pressure, phase transitions at high pressure, chemical bonding, theoretical calculations and predictions, interactions of cations with each other, the role of anions, synthetic analogs of known minerals, and predictions for the future. And there have been many colleagues and friends who have contributed to this work. I want to start off with wollastonite. Wollastonite is a material that was a subject of my PhD thesis. And it all came about because Professor Berger, who was my advisor at MIT, had worked on pectolite, and he had tried to solve the structure of wollastonite, but was unsuccessful. He thought it was going to be the same, have the same atom coordinates as in pectolite, but it didn't work. And then Mamedov and Bielov published a paper. I don't know how to point. I don't have a pointer. I guess I'll just have to wave my arm. Oh, here it is. Here it is. I forgot how it works. Okay. This is Mamedov and Bielov. Also, Professor Ito in Tokyo was working on wollastonite as well. And we went through this whole series of studies of this material. This is a picture of Professor Berger and his wife Lila. And this is a publication containing papers by Ito. I don't have a photograph of Ito to show. He was working on the structure of wollastonite. And this is a photograph of Bielov, who was one of the most productive crystallographer mineralogists in the Soviet Union at that time. Both Ito and Bielov came to MIT to visit Professor Berger, and I was quite intimidated as a student by the two of them because they knew so much about minerals and mineral structures. And then I went ahead and figured out the difference between pectolite and wollastonite. We published refined crystal structures of the two and began my career in crystallography. After that, I became more interested in the calcium silicate series. Wollastonite at low pressure is here, and it transforms to wallstromite, and I'll talk about that in a minute, then breaks up into two phases at higher pressure, and then finally to perovskite. There are two red dots here. These are pseudo-wollastonite phases, which we did the structures of. And people were very confused by this material for a while because it was usually disordered, and it was hard to get good diffraction patterns. But we were able to do that, and this shows the results. And this is the series of calcium silicate phases of various kinds. I'll say something about the Goldschmidt structure. It was originally known as Ca2Ba Si309, and Troyer, who was also a graduate student with Berger, solved the structure of the high-pressure phase of pure calcium silicate, and we later found out it was the same structure as Goldschmidt. It has been found as a natural mineral in a diamond from Guinea, and we also looked at other compositions of strontium and germanium, and I'll show something about that in a minute. This is the structure of strontium germanate 2, and it is the material published by Nozdazina. My point here is that there are all these phases still out there that have not really been described in a comprehensive way. So if someone wanted a research project today, it would be very useful to go through and look at all of these silicate and germinate phases. Now I want to go on to radii that was mentioned earlier. I was very pleased to be able to come for this ceremony at the Goldschmidt meeting because Bob Shannon and I really followed Goldschmidt in preparation of our tables of ionic radii. Most of the good ideas came from Goldschmidt and Pauling, and we published, this is the Goldschmidt and Pauling set of radii, and this is a page from our set of effective ionic radii. And we did several things that were different, which I think made our radii more useful to people in the field. We divided them up according to coordination number, and we looked at high spin and low spin variations, and we also stuck to oxygen and fluorine as the anions in the phases. And I believe this has been quite useful to people over the years, and there are still things that must be done. For example, people keep asking me, why don't we have tables of radii as a function of pressure? Well, that's a very difficult problem, but some people are thinking about how this information could be presented for use by people working in the field of high pressure. Another application of the radii is to plot the radius of cation A versus the ratio of cation A to B. And this is a very useful way to show how the various compositions vary. And it turns out that, for example, the lanthanum aluminum oxide phases fall on lines such as this. And it's just very easy to characterize what's going on. Rodi and Babo published the synthesis and structure of the calcium iridium oxide post-perovskite structure. Notice it's 1965. And that's maybe 40 years before anyone actually thought about that as a possible mineralogical high-pressure phase. Another thing that one can do, and this is related to my previous comment, that if you divide all of these phases on a diagram such as this, you can see that the crystal structure is a function of the ratio of cation sizes. And if someone were to really go through and characterize all these phases, this would be a good starting point to do so. The other thing that we included in our tables of radii are the cations as a function of spin, high spin, low spin transition elements. And when we published the radii, there wasn't a whole lot of interest in high spin, low spin. We weren't really involved in high pressure, single crystal, or other kinds of experiments where you could induce a high spin to low spin transition as a function of pressure. And people had not really looked at the interior of the Earth with the idea that high spin, low spin transitions could take place. But this has become much more a valuable tool in current research. Now, what I wanted to show here too is this is a plot of radius versus log of z over n. Z is the valence and n is the coordination number. And what we found is that the high spin cations really do fall on a straight line, and this is true of the other transition elements as well. And that the low spin radii fall on a straight line parallel to the other line. And one thing that came out from this plot is that in our original radii, we obtained the difference in radii of iron in high spin and low spin from the sulfides, because we had no oxygen related material to look at that time. And troilite and pyrite are the two sulfides that we looked at. And it turns out that using pyrite, which gave us this number, was not a good thing to do, because the disulfide aspect of pyrite makes the FES distance shorter than it would be in a single low spin situation. So if you have a table of radii from Shannon and Prewitt, or from Shannon, go to your ferrous iron in low spin octahedral coordination and move it up to this point here. Now, here's something I think this is interesting. I don't really know who first thought of silicate perovskite as being a viable phase. I know that Dave Mao and Raymond Jeanlo were thinking about it, but the person who really came out with the definitive information on perovskite with silicon and 6 coordination was L.G. Liu, and in particular the second paper had lots of information about perovskite and its character, and show that this is 1976. And I showed you before that at that time we knew about the Rhody, the one that I showed before, post-perovskite structure, but nobody paid any attention to that. And this is from the cover of Science in 2004, where Murakami et al. Described their discovery of the post-perovskite structure. And I think that was one of the very exciting, most important discoveries in high-pressure mineralogy that we will ever have. Maybe we will find other things, but I think that's very important. Rhody and Babel published this paper in 1965, and we didn't know about silicate perovskite until 1975. This is the structure, of the calcium iridium. And if you look at that diagram I showed previously with the plotting the radii of A versus A over B, you can see that the calcium iridium falls right over perovskite itself, calcium titanate perovskite. So it's amazing that no one looked at it and thought about it as a possible high-pressure mineral phase. This is another picture of the post-perovskite structure, and I'm going to show another diagram about characterizing it. The thing that I think is really interesting in this is that the magnesium is in bicap trigonal prism coordination. Most people don't seem to realize that. They call it dodecahedral or something like that. But it's a very regular, highly symmetric material. It's more symmetric than perovskite itself in terms of its symmetry. Now, I said people don't really realize that it's trigonal prism. This is a bicap trigonal prism in post-perovskite. And you see it has 6 short distances of 1.95 and 2 long ones of 2.07. You can also look at it as a distorted square antiprism, but that's really not the symmetry. This is the real symmetry of that site. Then if you go back and look at perovskite, most people don't consider perovskite itself as a bicap trigonal prism. It's more distorted than the post-perovskite, but you can see there are 6 magnesium oxygen distances, 2.12 angstroms, and then 2 others at 2.43. It's clearly a very similar coordination to the post-perovskite. And you can characterize the post-perovskite as 2 columns going in the same direction. This is a trigonal prism column with the trigonal prisms sharing faces with each other. And this is the octahedral column. And it's really highly symmetric in terms of just these units in the structure. Now, Umamoto and Wenskevich published a paper and gave a talk at the spring meeting of the American Physical Society last year. And they found that the FeUS3 structure has the post-perovskite structure, and it's very similar. You see the bicap trigonal prism here and the octahedral site for the silicon. Then they talked about a post-perovskite structure. If we go to another planet with much higher pressures in the interior, this could be a very useful analog of a post-perovskite structure. And it has a bicap trigonal prism, just like that one, but the other site is a monocap trigonal prism. So you're increasing the coordination, and it made me think of a structure I worked on years ago when I was at the DuPont company, and we were making rare earth sulfides for various reasons, and one that I worked on was GT2S3. It has a monocap trigonal prism for one site and a trigonal prism for the other. And one thing one can do is search through possible radius ratios of oxides at high pressure and make a structure that would be this structure. It's not out of the question that there are other high pressure phases in the oxide system that could be found within the Earth or at other high pressures. Now I want to move to looking at trivalent cations. This is where we would have 2 trivalent cations in the ABX formula. And these are the red or orange squares are all ions that can occur in the trivalent state. And one structure that I've been interested in for many years is corundum. And corundum is an interesting structure because you have octahedra that share faces with other octahedra in a pair, and there are electronic interactions across the shared face. And each octahedron also shares 3 edges with 3 surrounding octahedra, and there is a chance for electronic interaction there, particularly among the transition elements. These are the known first row transition element sesquioxides, and one was just reported this year by Ma and Rossman, a titanium Ti203, pronounced tistarite, with the corundum structure. And then all of these others occur as minerals. Bixbyite is not quite the corundum structure. It's a sea rare earth structure. And I've been interested in these phases at both high temperature and high pressure. And this diagram shows a cation radii in decreasing size, and each of the ones with an arrow are known to occur in the corundum structure. And I'm not going to talk about all of the high pressure work that's been done on these phases, but Stan-Olsen et al. Published a paper where they saw a phase transition in Fe2O3 about 50 GPa, and they said the high pressure phase was perovskite. Then Pasternak et al. Did Mossbar spectroscopy and electrical conductivity measurements and found that it could not be corundum structure, could not be perovskite structure. And the reason it could not be perovskite is there is only one cation, and it also indicates a high spin to low spin transition. So they knew it was not corundum, and I want to come back to that. I'll leave it there. I'm showing this because there are transition elements which are trivalent that have both high spin and low spin configurations. So there's manganese, iron, cobalt, and nickel that can have both high spin and low spin configurations. Saint-Elon et al. Did a study of Mn2O3 and found out there was a phase transition at about 25, 26 GPa, and it turns out that it goes to the post-perovskite structure between these pressures at 2000 K. Transition to Mn2 plus and 8 coordination plus Mn4 plus and 6 coordination is a possibility, but it's more likely that it goes to Mn3 plus high spin and Mn3 plus low spin. I also put this in here because, as far as I know, no one has done high pressure work on these compositions, and they contain iron 4 plus. And so it would be interesting to see what happens to these two phases at high pressure. So some young person here can work on that. Then I want to go to the Fe2O3 structures. And as I said, Stan-Olsen et al. Thought it went, Fe2O3 went to the perovskite structure at high pressure. And then we showed that it did not. It goes from hematite to the RH2O3 structure and to post-perovskite. And Bob Shannon and I, a number of years ago, published the structure of RH2O3, which has a unique structure. And if we had not done that with a single crystal determination, it's very probable that everyone would think that the intermediate structure is perovskite. Don't want to go. Now, there's a lot of material here on Fe2O3. Rosenberg et al. Look at Fe2O3 at pressures up to 76 GPa at room temperature and found a transition at about 50 GPa from hematite to the RH2O3 structure. And they perform Rietveld refinements in public interatomic distances and angles for these high pressure phases at room temperature. Ono and Ohashi reported a transition in Fe2O3 to post-perovskite at 60 GPa and heating up to 2000 K. And they published the results, obtained at 68 GPa after quenching from high temperature. So I'm not going to go through the rest of this in detail. I'll show you the next diagram. Rosenberg, what I've done here is put the radii, plotted the radii from our tables at 0, and then plotted the experimental results for each of the experiments. The Rosenberg experiments are here, this one here and this one. And their conclusion was that this was ferric iron in 6 coordination and low spin. The Ono et al. Work presented these results, in which it appears that iron 3+ has gone from, it probably went through the RH2O3 structure and then to the post-perovskite structure with iron in 3+ and 8 coordination. And the other site would be iron 3+ in 6 coordination low spin. The problem here that I haven't been able to figure out is that this is octahedral 3+ iron in low spin configuration, and this one is supposed to be as well. And the real question is, why are they so different? I haven't figured that out. And the other thing I just wanted to put is that if we had iron 3+ in 8 coordination in low spin state, it would be this size. But it's very unlikely, probably impossible, for iron in 8 coordination to be in the low spin state. And there's one more puzzle in the transition metal oxides. Chenevas and Joubert published a paper back in 1971 with low spin CO2O3 synthesized at 90 kilobars and 1,000 degrees. And they determined that it was low spin cobalt. Then they annealed it at 400 degrees C, and it transformed to high spin CO2O3. And the single crystal was preserved in this experiment. And several prominent people have told me that, I don't want to do that yet, they have tried to duplicate this experiment and have not been able to. So it's still something that someone needs to try again. Yeah. Okay, I have one more item to present to you. I had a graduate student who worked, Jadon Ko, who was interested in high pressure studies, and he synthesized MnTiO3 at high pressure and found that it had the lithium niobate structure. And the lithium niobate structure is characterized by having the cation pairs, the manganese titanium vectors, all pointed in the same direction. whereas ilmenite would have half of them in one direction and half of the other. And I just got an email from Ahmed El-Garazi saying that they have found FeTiO3 from the Reese crater that has the lithium niobate symmetry and structure rather than ilmenite, as previously thought. So this undoubtedly is a result of shock, high pressure transition in FeTiO3. And Ross, Coe, and I published this paper in 1989, characterizing the MnTiO3 in detail. Well, I want to just say two things about the future of mineralogy. I've been quite impressed by the paper by Hazen et al., an American mineralogist, with a different approach to teaching mineralogy. This is starting from the creation of the solar system and how minerals evolved from the very beginning and why they evolved the way they do. And I think this is a really interesting new way to think about mineralogy. And the other one is Gibbs et al., who are really advancing the understanding of bonding in minerals. And I think when you see their paper and get an idea of what's going on, and not only just oxides or fluorides like our radii are involved, they're really doing a good job of looking at bonded interactions in silica polymorphs and other materials such as arsenides and sulfides. So, in summary, I think there will be many more exciting developments in the future, and thank you for listening.